Good morning. So I'm excited today. We begin the second half of the course today, which of course means, yes, today's lecture won't be on the midterm. So, okay, the usual question. But no, seriously, I'm excited because now we get on to the topic that I hinted back way in lecture 2. I said that basically the bulk of this course is covering carbonyl chemistry. And even beyond lectures, the 6 weeks of the class, we continue with the theme of carbonyls in the very end of the class where we talk about carbohydrates and about peptides and proteins. But we've been talking for the past essentially 5 weeks about the electrophilicity of the carbonyl group. And now we're getting into this second half of carbonyl compounds, the fact that they're nucleophilic at the alpha carbon under the right conditions. So back in our first week, I drew a diagram sort of like this. I said, okay, here's some generic carbonyl compound, not necessarily a ketone or ester, or aldehyde, we could mean an ester. And the general gist of it is that the carbonyl compound is electrophilic. It can react with nucleophiles. And now we come to this second half, and so I'll say, now we bring in this notion that the alpha carbon, under the right conditions, can react as a nucleophile. In other words, it can react with electrophiles. And we're going to be exploring this idea extensively over the next 4 lectures. We're going to be spanning this idea from chapter 23 in your Smith textbook to chapter 24 and discovering the richness of the chemistry of enols and enolates, which are the intermediates by which we have this reaction. Okay, so we talked before about various aspects of carbonyl compound structure, and we talked about the reactivity of a carbonyl compound. We talked a little bit about, in water, equilibrium with a hydrate species, and we said that, for example, in acetone, there's very little of the hydrate. And typically, it's not a big factor in the behavior. In other words, if I took an NMR spectrum of acetone in water, I wouldn't see the hydrate because it's just a minuscule amount of the compound. Well, there's another minuscule amount that can be present that's very important in reactivity, and that is the enol tautomer. So I'll write an equilibrium where we have, and let's just take this as acetone right now. We'll be going through with various examples, but let's just pretend you have acetone or some ketone or aldehyde, let's say. And so we have this equilibrium where we have another species, and now the species is obviously very different. In other words, you have the carbonyl compound, and then you have a species that has a double bond and an alcohol, and that's why it's called an enol, because en means a double bond and ol means alcohol. And so we refer to this as the keto tautomer, and this as the enol tautomer. So Tautomer means an isomer where you've moved hydrogen around. And so you notice, of course, if this is acetone here, we have 3 hydrogens attached to this carbon. And then in this particular enol of acetone, we would have 2 hydrogens attached and 1 here. So that's the same formula, it's the same molecular formula, and yet a different arrangement of atoms. Tautomers are a type of constitutional isomer. Remember, we've learned about stereoisomers, and then we've learned about constitutional isomers. And by constitutional isomer, I mean we have a different connectivity. Stereoisomers have the same connectivity. Now, as I said, the enol tautomer is in equilibrium with the keto tautomer, and that equilibrium lies way, way to the left. I'll tell you just how far to the left in just a moment, but I wanted to introduce our players. Now, if we imagine pulling off the hydrogen of the enol tautomer, in other words, deprotonating, removing that hydrogen with a base, we get what we call an enolate anion. And I'll be sort of semi-generic here. In other words, we could be acetone, we could be something else, but I want to show you that there are 2 substituents attached to the carbon of the double bond there, to what we call the alpha carbon. And the enolate anion can be thought of as having 2 different resonance structures. So we can envision one resonance structure where we have our negative charge on the oxygen, and a second resonance structure where we simply move these electrons down and move the electrons onto the alpha carbon. Remember, we use a double-headed arrow, not a reaction arrow, not an equilibrium arrow, but a double-headed arrow to indicate resonance structures. And I will very explicitly draw my lone pairs and draw my negative charges like so. And just to be a good person, I'm going to put this in brackets to remind us, to help remind us that these are 2 pictures of the same thing. It's not one, it's not the other. Unlike the ketol and enol tautomer, they are not 2 distinct species that you can identify distinctly. They are one and the same at the same time. And so I will write resonance structures here to remind us of this. And I will also remind us that since this is the anion of an enol, we call it an enolate anion. All right, and these 2 sets of variants on the carbonyl, the enol tautomer and the enolate anion, are going to be occupying our thinking for the next couple of weeks, for the next 4 lectures, as we explore the reactivity of carbonyl compounds, and specifically their ability to react as nucleophiles at the alpha carbon. All right. In terms of understanding reactivity, and this reactivity as nucleophiles, I think the enolate is a very obvious place to start. So if I draw the structure of an enolate, like so, and again, I'm keeping it kind of generic. You could think of this as acetone enolate, or you could think of it as some other enolate, but in fact, this is pretty much universal behavior of enolates. And we imagine some electrophile. Now, again, in the spirit of keeping things generic, I'm going to write it as E+. That doesn't necessarily mean we have a positively charged species. You've seen positively charged electrophiles. You've seen carbocations in the past. Protons, or H3O+, of course, are cationic electrophiles. But by the end of today's lecture, you'll also be seeing methyl iodide and SN2 type alkylating agents acting as electrophiles. So here in very cartoony, very loose fashion, I'll write E+ in quotation marks. And the reactivity at the alpha carbon as a nucleophile can be thought of as bringing our electrons down from the oxygen, bringing our electrons over from the double bond over to the atom bearing the positive charge. I guess technically, if I want to do this right, my arrow should end up at the atom. And again, this is sort of an abstraction of an atom. And so if I want to complete my drawing, that constitutes our reaction. Now, if you're not comfortable with moving all of these curved arrows around, realize that this is just the representation, that this first part of moving electrons down and moving these electrons is just the embodiment of how we get from the resonance structure on the left to the resonance structure on the right. In other words, when I'm interconverting these two resonance structures, in my mind's eye, I'm bringing these electrons down and bringing these electrons onto the alpha carbon. But I don't necessarily need to draw that out, because by this point in my course and by this point in your thinking, you should be comfortable enough with that operation in your mind. Okay, so that constitutes the reactivity of enolates, and I just want to take a moment before I take questions to talk about the reactivity of enols, again, overviewed in this very, very generic fashion. So in the case of an enol, this minor species that's present in equilibria with ketones and aldehydes, and to a lesser extent with other carbonyl compounds, we can imagine here's our enol, and again I'll have my generic electrophile, E+, and we can imagine electrons flowing down from the oxygen into the carbon-oxygen bond, giving rise to a carbon-oxygen double bond, concurrently with electrons flowing from the carbon-carbon double bond to the electrophile. And if we continue with our grammar of electron pushing, our grammar of the curved arrow, now that's going to leave us with a protonated carbonyl and a bond to our electrophile. And now we can imagine losing a proton. Again, I'm talking very much in abstractions here, so I'm not talking about a proton just popping off, but a proton being taken off by base. And so at this point, we can imagine going ahead and getting to, and I'll write that proton in quotes because, again, one would envision something taking it off. So we can envision getting to the carbonyl compound that's reacted at the alpha position. Question?
Yeah. Can the negatively charged carbon also grab the electrophile to form the same product?
Can the negatively charged carbon? Absolutely. It is one and the same. Whether I write this reaction as a flow of electrons like such, or whether I write the reaction as, I guess again, technically to be correct, since it's a resonance structure, I'm going to write it in the exact same geometry, the exact same geometry, because the two resonance structures share a geometry. Okay, if I want to think about it like this is the self-same thing. It is the exact same way of writing this, and so these are not really different, they're just different ways of representing the same thing. And as one moves in their understanding of organic chemistry, you go from sort of needing to explicitly write that latter one out to recognizing that the one image embodied in the former, which happens to be the major resonance structure, the one image embodied in the former ends up being enough for us to think our way through. Other questions? All right, let's move on to some specifics. So this provides an overview. This provides a very generic introduction to the chemistry of enols and enolates. And now let's talk a little bit about some specifics about the prevalence. Of all the carbonyl compounds, with the exception of dicarbonyls, which we're going to talk about very soon in a lecture or so, with all the carbonyl compounds, aldehydes and ketones are the most enolic, with aldehydes being a little bit more enolic than ketones. Your textbook just gives sort of a generic answer that there's less than 1% enol present for a typical carbonyl compound, but it's a lot less than 1%. There's very little enol. So acetone is an equilibrium. If you spray acetone on your glassware, you're spraying mostly acetone, but you're spraying a little bit of acetone enol. It's an equilibrium, and the position of that equilibrium, K is equal to the equilibrium constant, is equal to 1.5 times 10 to the negative 7. In other words, there's less than 1 part in a million of acetone enol present at equilibrium. Cyclohexanone, in general, more substitution makes for a more stable double bond. We learned this in the chemistry of alkenes, that in general, when you put alkyl groups on a double bond, it's more stable. So cyclohexanone exists in equilibrium with the enol, and it's a little bit more enolic than acetone. The equilibrium constant is 5 times 10 to the negative 5. Again, just a hair more than 1 part in a million, whereas before I guess we had a hair less than 1 part in a million. As I said, in general, aldehydes are a little bit more enolic than ketones. That's not necessarily surprising. Remember, the aldehyde carbonyl group is pretty darn unhappy as a carbonyl group. It's only got 1 alkyl group donating in. We saw this when we talked about the chemistry of hydrates, and we said that acetaldehyde exists about 50%, about half hydrate and half as the aldehyde form in water, whereas acetone is vastly predominantly the ketone form, not the geminal diol. And so similarly, we see that acetaldehyde is a little bit more enolic than, say, acetone, which would probably be the best comparison. So in acetaldehyde, you again have an equilibrium. Again, that equilibrium lies way, way to the left. But now you have just a hair more of the acetaldehyde enol. The equilibrium is at 2 times 10 to the negative 5 for your equilibrium constant. So compared to acetone, a couple orders of magnitude more. in spite of being a minor equilibrium component, the reactivity of enols is very important in the reactivity of carbonyl compounds. So that makes sense. Even if you have a little bit of something, when it reacts, more gets generated, and so a reaction can proceed and proceed and proceed. Being small doesn't mean you're unimportant. And so we can take a look at how enols and ketones, keto and enol tautomers interconvert and look at the mechanisms of formation. Another question?
So does formaldehyde has more like a more enol form because it's unstable?
All right, who wants to answer this question? Someone. Enol form of formaldehyde.
Sorry.
Can't. No alpha carbon on formaldehyde.
Sorry. Not the formaldehyde.
Acetaldehyde. So
Does acetaldehyde has more like enol counterparts and its acetone counterpart because acetone is more stable?
that's a very good way of thinking about it. Whenever you have an equilibrium, you're comparing the energy of a ground state and a product. And so the bigger the difference in energy, the bigger the equilibrium constant, the bigger whether it's positive or negative, depending on, whether it's greater than 1 or less than 1, depending on how the energy difference goes. So anything that either lowers the energy of the reactant or raises the energy of the product makes that equilibrium constant greater in magnitude, whether it's in one direction or the other direction. So when we talked about acetone versus cyclohexanone, they're both ketones, but we're lowering the energy of the enol by making the double bond more stable. So here's the acetone enol, here's the cyclohexanone enol. In the case of acetaldehyde versus acetone, now you can think of it as we're raising the energy of the reactant because acetaldehyde is higher in energy. It's less stabilized relative, and it's always a question of reference frame. But that's a good way to think about it. So later on, we're going to see things that provide a lot of stabilization of the enol, specifically conjugation. All right, so that's talking about reactants and about products, about keto and enol tautomers. Let's now look at how we get from the keto tautomer to the enol tautomer. And this reaction can be catalyzed by either acid or base. I want to start off by talking about acid-catalyzed enol formation. And I'm going to write out the mechanism very slowly and carefully, very meticulously, because I think this really is important to think your way through. We've already seen on the quiz how important mechanism is, and clarity in expression and thinking on mechanism. The mechanism on the quiz was kind of long and complicated, involving many steps. The mechanism of acid-catalyzed enol formation is relatively simple and easy. If you have an acid, hydronium ion, for example, protons go on and off everything with lone pairs of electrons. The carbonyl of acetone or the carbonyl of a ketone or the carbonyl of an ester is weakly Lewis basic, weakly Bronsted basic. And so you have an equilibrium where you can protonate the carbonyl. If we're looking at hydronium ion as catalyst, hydronium ion has been consumed in the first step of this reaction, and now we're going to recreate it in the second step of the reaction. I'm going to again draw our protonated acetone. And now I will explicitly draw in my alpha hydrogens because we're going to use them very often when you're writing a mechanism or thinking about a mechanism. You will write different parts of a molecule at one time. So here's our water. Here's our alpha proton. And now water is weakly basic, very weakly basic. Water can pull off the alpha proton. We just push our electrons up on to the oxygen, and again we have an equilibrium. Whoops. And I will be very, very explicit and try to draw in all of my relevant hydrogens here to help keep us on track. And I will try to remember all of my lone pairs and all of my charges, so I'm not a bad person. And here we go. That's an example of how we go from the keto tautomer to the enol tautomer. Thoughts or questions at this point? Is water able to pull off the hydrogen? So you mentioned the term addition elimination. Now we've seen addition elimination in acid chlorides. That's where a nucleophile adds to a double bond. We kick up a lone pair of electrons. It comes back and pushes something out. Nucleophile, like an amine, adds to an acid chloride. We kick electrons up onto the oxygen. They kick back down, kick out the chloride. So this reaction mechanistically is an acid-base reaction. And the only thing that's maybe surprising or confusing to you is the fact that we're continuing to push our electrons all the way up. Now, technically, I could go ahead and stop at this point. But of course, if I stop at this point, I recognize in my mind's eye, well, this is a really, really funny resonance structure, a really unimportant bad resonance structure of that. And so we just keep pushing. And of course, protons come on and off all different acidic positions in acid-base equilibria. And so the proton, whoops, I forgot my positive charge. So much for being a good person over here. So the protons can come on and off the oxygen, then we head in the reverse pathway. And guess what? Most of the time, your equilibrium partitions back. In other words, when you have an equilibrium like this, so here's our energy, here's our reaction coordinate. When you have a reaction like this, where we're going from reactant, from our acetone plus H3O plus to our protonated acetone, and then to the enol. And technically, if I'm writing this out correctly, this is acetone, protonated acetone plus H2O. What's happening in our mechanism is first we're going uphill to an intermediate, and then we're coming down to our product, to our enol that's higher in energy. So when you're at this point, at the intermediate, you can partition back, you can partition forward. It goes both ways. Most of the time, it actually ends up going back down. And ultimately, of course, it's the difference in energy between our product and our reactant that determines the position of the equilibrium. There was another question.
Yeah, can you explain why the water can take off an H from the bottom left structure and it doesn't take the H from the
It does indeed take the H from the oxygen. And the mechanistic reverse of this step is taking the H from there. Most of the time, it takes the H from there. Some of the time, we go forward and it goes in the other direction. Or should I say, well, it's not technically the partitioning, it's not going to be most of the time. It's going to be half and half, because most of the time we're not forming this intermediate. So technically it can be a little more of one or a little bit more of the other. But the point is that heads us back. Sometimes we pull off this proton and it heads forward. This proton is acidic. Other question?
Can the water also perform a nucleophilic attack on the electrophilic carbon?
Can the water also perform a nucleophilic attack? Great question, and this is what's so profound. This is why people can find organic chemistry confusing. Because yes, it can, and yes, it does. And we saw that. We talked about acid-catalyzed hydrate formation, acid-catalyzed geminal diol formation. So in your acetone in water with a little bit of acid, honestly, even without a little bit of acid, because water has hydronium ion, 10 to the negative 7th molar, in your acetone and water, there is this gamish, this mixture of acetone, the main component, and then a little bit of the hydrate, and even less of the enol. So absolutely. And so keeping this in one's mind, oh yeah, this is the pathway we're thinking about now, because this leads to the good stuff we're going to see over the next 4 lectures, is often confusing to beginning students. Great question. Really important, because this is the part of understanding it all that's okay. And you look at this mechanism here, this manifestation of catalysis, and realize what this means for the uncatalyzed mechanism. It means that in the uncatalyzed mechanism, you're not actually changing the difference in energy. I'm trying to draw this curve for the uncatalyzed mechanism between acetone and acetone enol at the exact same level. You're not actually changing the difference in energy between acetone and acetone enol. What we're doing is providing a low energy pathway that's not accessible without acid. In other words, there is hypothetically a one-step mechanism that converts acetone to acetone enol, but the energy barrier is much higher. So when any acid is present, and that includes that 10 to the negative 7th molar H3O plus hydronium ion in pure water, acid can catalyze this reaction. Now, the other thing, and I've been beating on this like a dead horse. And the other thing that's important is reactions proceed through the reverse reaction proceeds through the exact same mechanism. When cyanohydrins form by adding cyanide to a carbonyl to give an oxyanion, and then protonating the oxyanion to get the alcohol, we learn that cyanohydrins break down under the same conditions by deprotonating the oxygen to give an oxyanion, and then kicking out cyanide. When enols form by first protonating the carbonyl to give a protonated carbonyl compound, and then deprotonating the alpha carbon to give the enol, that means that the reverse pathway proceeds backwards by the same mechanism. And so we can write, and you should be able to write in your sleep, the reverse mechanism. We simply go ahead and start with the enol and hydronium ion protons flow, the proton goes to the alpha carbon, electrons flow down from the oxygen, and now in the second step, that's the step in going from our intermediate in water back to our acetone. Now water just acts as a base and pulls off the proton on the carbonyl. Electrons flow from the lone pair on water to the protons. Electrons flow from the bond back onto the oxygen. Thoughts or questions? All right, let's see where this gets us in terms of some reactivity. And then we'll get to enolates, which get really fun. All right, I'm going to take probably the simplest reaction that I can think of. And that reaction is going to be deuteration. So let's take cyclohexanone as a variation here. And we'll envision dissolving it in D2O. I'll put parenthesis as solvent. D2O is just heavy water. It's just deuterium oxide. It's just the isotopomer of water with deuterium. Every glass of water you drink contains zillions of molecules of deuterium, or zillions of deuterium atoms. 1 out of every 7,000 hydrogen atoms is deuterium at natural abundance, meaning in your proteins, in your lipids, in your carbohydrates, there is a minuscule amount of deuterium, and one can, by electrolysis or distillation, concentrate the deuterium to get pure D2O. If we treat our cyclohexanone with D2O and a little bit of catalytic acid, I'm going to get away from H3O plus and D3O plus for a second to remind us one actually has to go into the laboratory and get a real compound. I've written DCl. DCl is just hydrochloric acid made with deuterium. So it's a strong acid. It dissociates in D2O. What will happen is you will replace all of your alpha protons with deuterium. And this is kind of cool. You could see this for yourself. If you asked your lab TA to give you some cyclohexanone and some D2O, and a little bit of DCl, and you dissolved your cyclohexanone in D2O, you would be able to take an NMR spectrum, and you would see the alpha protons, the hydrogens next to the carbonyl, at about 2.5 parts per million. And as the reaction proceeded, the peak in the NMR from those hydrogens, the peak at 2.5 parts per million, would disappear as those hydrogens were replaced by deuterium. All right, so how does this occur? Well, it's the exact same mechanism that we saw before, just repeated over and over again. I'll write this in abbreviated fashion. We can envision that in D2O, we protonate the D2O with DCl. Remember, when you pour HCl into water, you have H3O plus and Cl minus. The D3O plus is just like H3O plus in its reactivity. You can put a deuterium onto the carbonyl to give a protonated, or in this case, deuterated cation. And now in the second step of this reaction, of course, if I'm balancing my equation, in my second step of my other product is D2O. In the second step of the equation, just as we have pulled the protons off the alpha position of acetone with H2O, alpha protonated acetone, now the D2O can pull off our alpha protons, and so again we have an equilibrium. Now we take ourselves to the enol plus, if I want to balance my equation, D2OH plus. All right, I think I will continue on the sideboard here. All right, so one thing I should point out is we have lots and lots of D2O present. Water is 55 molar. Deuterium is practically the same as water. D2O is going to be essentially 55 molar. Protons, as I've been saying again and again, go on and off every protonated species. In other words, when we have D2O, H plus, and lots of water, so I will write plus excess D2O, you have an equilibrium, and of course mass action drives this equilibrium. And so you'll get a little bit of H2O, HOD, plus D3O plus. In other words, basically you've got tons and tons of D2O. Your water just spreads out, your protons just spread out to make little bits of HOD. If I do a reaction with 55 molar D2O and I have a 1 molar solution or a 10th molar solution of ketone, as my protons go in, I get this little bit of HOD in this mass of D2O and D3O plus. All right, let's continue our mechanism here. So we have our enol with a deuterium on it, and we have lots and lots of D2O and a little bit of D3O plus. We can protonate our enol. I'm just writing the same mechanism as I wrote before without the curved arrows and without filling in all of my lone pairs of electrons. And now we can have further deuteron transfer And you can envision this mechanism just continuing. We form the enol. We protonate the enol with deuterium. We form the enol some more. We protonate with deuterium. And eventually, we've washed out all of those enolizable alpha positions. And now we have the fully deuterated molecule. And organic chemists are terribly bad at balancing equations, but if I want to write a balanced equation, I would write that our ketone plus 4 D2O goes with catalytic DCl in D2O solvent goes to the fully deuterated ketone plus 4-HOD in lots and lots of D2O. So one of the other properties of carbonyl compounds is that their alpha proton is acidic. So for example, in acetone, the alpha proton has a pKa of about 19. And that's interesting, because if you think about it, if you think about, say, a regular methyl compound or a regular alkyl compound, the pKa is about 50. In other words, the pK of an alkane is, while nominally acidic, very weakly acidic. It is very, very, very weakly acidic. It's only acidic in the sense that you can think of its conjugate base as being a very, very, very strong base. And yet, by the time you get over to acetone, putting that carbonyl there shifts by 31 orders of magnitude the acidity of that proton. It shifts the equilibrium massively, because when I think of the conjugate base of acetone, I don't just think of this. I think about that special resonance stabilization that we get as the enolate. And you can see how picturing these two resonance structures together, the structure on the left is really very inadequate to explain this stability. The structure on the right explains it beautifully. We have a negative charge on the oxygen. We have oxygen is electronegative. We know alkoxide has, or alcohols, are reasonably happy to lose a proton. They're weak acids, but they're not very, very, very weak acids. pK of an alcohol is 16 or 17. The pKa of an alkane is 50. That oxygen does a heck of a lot. And with acetone, with our pKa of 19, we're getting a lot of stabilization from this resonance structure. In other words, this is the major resonance structure. This is the one that's important in determining the reactivity, and this one is the stability, and this one is the minor resonance structure. Now, more generally, the carbonyl group provides stabilization. And your textbook gives a number of compounds, and I'll give you these compounds, and then I want to give you a generalization that I keep in my own head. So your textbook gives you acetaldehyde with a pKa of 17, and it gives you ethyl acetate with a pKa of 25 for the methyl group, and acetonitrile with a pKa of 25, and dimethylacetamide with a pKa of 30 for the alpha proton. And really the numbers that I keep in my head, these are a lot of details, but the numbers that I keep in my head are as follows. I keep in my head two numbers for all of this. That the alpha protons for the ketone and aldehyde family are about pKa 20. Twenty's good enough. Yeah, I'll keep in the back of my head aldehydes are a little bit more acidic. I'll keep in my mind that 20 is typical for, say, cyclohexanone, that acetone is 19. But those details are small. Those are unimportant. The other big picture, while aldehydes and ketones are about pKa 20, in general, the carboxylic acid family esters, nitriles, even amides, even carboxylic acids under the right conditions. You first remove the acidic proton, so it's a carboxylate, and then you remove a second proton. In general, a good number to keep in mind is about 25. Yeah, there's some variations, but it's not as super important as keeping these pictures in mind. And one of the pictures from this is, in general, ketones and acid and aldehydes are less acidic than water. In other words, hydroxide will take off only a small amount of the protons, only an equilibrium concentration. Ethoxide will pull off only an equilibrium concentration. But stronger bases, those can pull off protons quantitatively. Since the alpha protons of ketones and aldehydes are acidic, it shouldn't surprise you that base can also catalyze enol formation. So let's come back to our acetone molecule as our sort of archetypal ketone. And now let's envision hydroxide as a base. I could do this with alkoxide too, but some sort of moderately strong base, not super, super strong. We'll talk about super, super strong in a moment. But something like hydroxide or an amine like triethylamine. We can pull off the alpha proton. The alpha proton is weakly acidic. Remember, pKa of 20 is the number you want to keep in your head. So we have an equilibrium here with the enolate. But that equilibrium lies slightly away from the enolate, and so we can protonate. In other words, you generate a little bit of enolate, but that you don't generate the enolate quantitatively. And so we can protonate. If we protonate back on carbon, we're headed back in the same position. We're headed back to the start of the reaction. If you protonate on oxygen, on the other hand, now we've proceeded on to the enol. And just as in our acid-catalyzed enol formation, hydroxide here, although it's being consumed in the first step, is being recreated in the second step, and so it is not being taken up or destroyed or created in the reaction. Overall, it is acting as a catalyst. Similarly, we're not changing the position of the keto-enol equilibrium. We're only creating a lower energy pathway to allow the ketone and enol forms to interconvert.
Would there be more enolate in the solutions than enol, since the solution is basic and the water can be deprotonated by a base?
Okay, good question. If you're working your equilibria, technically, yes. In this particular example, that is an astute question. In this particular example, with these particular pKa's, technically you're right. There will be more enolate than enol present. If you want to come to an example where now you have very little enolate and the equilibrium still goes, substitute in this reaction as base triethylamine. Because now, remember we said that for acetone we're going to have 1.5 times 10 to the negative 7 is our equilibrium constant. So there's not a lot of enol. And we're having our pKa for acetone of 19, which means you actually do have, 1 in 1,000 or 1 in 10,000 enolate, 1 in 1,000. So if you substitute triethylamine, pKa about 10 or 11 for the conjugate acid, you'll still catalyze this reaction, but now you'll have very, very little of the enolate. Do you use a Dean-Stark apparatus? No need here. We're not actually trying to change the position. And, okay, could one? Now you're asking a smart question. Can one drive this reaction? And the answer is you can't drive it by removing water because the reaction is unimolecular overall. There's no net change in the molecule. It's an isomerization. So the way to drive the reaction to the enolate is to go ahead and to use a very strong base. And unfortunately, there's very little one can do to try to generate the enol as an isolated species, although there's an Israeli chemist who actually is focused on stable enols. Because another thing about organic chemists, in addition to being very bad at balancing equations, is if someone says, it can't be done, enols are unstable, you can't make a stable enol, you can bet you an organic chemist will go out there and say, how do I make a stable enol? We'll see some stable enols that are very special enols, but for a regular one. All right, so where is all of this leading? Let's go and do some enolate chemistry. So just like with DCl and D2O, if I take cyclohexanone with catalytic sodium deuteroxide, just the deuterium analog of sodium hydroxide, in D2O as solvent, and I let it sit, again, you can do this for real in an NMR tube. Johnny or Kim could go back to my laboratory and do this right now and show you those alpha protons would wash out and be replaced by a deuterium. Similarly, if I imagine for a moment that I had something that had chirality at the alpha position, let's imagine for a moment that I have this ketone where I have a methyl group. And let's say that I have just the S enantiomer. And I treat this ketone with, let's say, sodium hydroxide, since we're talking enolate chemistry, sodium hydroxide in water. Then what will happen will be I'll lose my enantiomeric purity. I will get a mixture of the two enantiomers. I will get the racemate. I will get an equal mixture of the R and the S. What's happening here in this latter example? We're forming little bits of the enolate repeatedly. The enolate is flat. The enolate loses its chirality. What am I doing here? Oops. I will say that we go via this. In other words, you can picture in your mind's eye, the base pulls off the alpha proton. We get the enolate. The enolate is flat. We have no chirality to the enolate. If a proton comes from the back, we get the original enantiomer. If it comes from the front, we get the new enantiomer. And so our compound racemizes in aqueous base. All right, so in addition to being bad at balancing equations, in addition to wanting to do what can't be done, organic chemists are control freaks. We want to control the molecules and make them do stuff, and often we want to do stuff to make stuff that's useful, like new medicines. So, whereas weak base doesn't make a lot of enolate, a strong base does, and we can use that. If you have something like cyclohexanone and a base, I'll write it as B minus, let's say, a very strong base. In other words, pKa of the conjugate acid much greater than 20. Then we have an equilibrium that lies way, way, way to the right, often so far to the right that we can just ignore the left arrow to give us the enolate anion and our protonated acid. And the base that's extremely valuable to organic chemists is diisopropylamide anion, or more specifically, the lithium salt, lithium diisopropylamide. And for those of us who are control freaks, for those of us who want to make molecules do stuff, this base is really good because it's a strong base. pKa of the conjugate acid, the pKa for diisopropylamine is about 40. So I'll write pKa IPR2, NH is a nice shorthand, and I'll say tilde approximately 40. Remember, we're comparing, I said if you want to keep one number in your head, keep 20. For the pKa of cyclohexane, for the pKa of a ketone, that's actually the pKa of cyclohexanone to within a unit. But again, just keep that number in your mind. The other thing that's really important about the diisopropylamide anion is it's big. Those isopropyl groups, and there are two of them, are bulky. They get in the way. In other words, lithium diisopropylamide is a good base, but not a good nucleophile. And again, I'm going to come down to this confusion in organic chemistry students when you're starting out. Oh my God, there's all this stuff to know. How do I know that this compound, like cyanide, is acting as a nucleophile? How do I know that diisopropylamide is acting as a base? Well, you start to learn these patterns. The very bulky ones are better at pulling off protons. The little bitty ones, and cyanide is just a little bullet, is better as a nucleophile. So the reaction here lies so far to the right that our lithium enolate, I won't even bother to write the reverse arrow. Our lithium enolate is essentially formed stoichiometrically, and of course the other component in this reaction is diisopropylamine. So we have an acid-base reaction. Stronger acid plus stronger base reacts to give weaker acid plus weaker base. How do you know where that equilibrium lies? You just look at the pKa's of the acid. Okay, we've got the weak acid pKa 40 on the left. We have a strong acid on the right. And remember, the other number I like to keep in mind is about 10 orders of magnitude. In other words, if you've got things within a pKa range of about 10 units, I'd say, yeah, you've got a little bit of an equilibrium. But you go to 20 units apart, and it's like, bam, that reaction goes essentially all the way. Often when organic chemists are writing out synthetic reactions, we'll write in a little bit of shorthand. For example, I will say LDA. It's widely used in tetrahydrofuran as a solvent. In order to minimize its reaction as a nucleophile and minimize equilibration processes, often you'll do these reactions at -78 degrees Celsius. That's the temperature of a dry ice bath, which makes it particularly popular. Remember early on I said that E plus is sort of an abstraction. I said you'd see methyl iodide. So you can envision a reaction like this. In the first step, we add cyclohexanone to LDA at -78 degrees. In the next step, we drip in methyl iodide and allow the reaction to warm up, maybe perform an aqueous workup on it with a little bit of acid, and we've methylated our cyclohexanone. What's happening here? Same thing we saw with protons. We've generated our enolate stoichiometrically. Here's our methyl iodide. Whether it's a proton, whether it's methyl iodide, we have a good electrophile. Electrons flow from the alpha carbon to the methyl, to the electrophilic methyl carbon, and we do an SN2 displacement. To give the methylated cyclohexanone and iodide anion. Most of the time, organic chemists don't go ahead and buy lithium diisopropylamide. We typically make it by acid-base chemistry. N-butyllithium is widely available. It's the most common alkyl lithium, widely used. You can mix it with diisopropylamine in THF if you like before you add your cyclohexanone, and you pull off a proton you get butane plus lithium diisopropylamide. And again, I'm now getting into writing things in shorthand, so I'm not writing as many lone pairs of electrons here. And this, too, is an acid-base reaction. N-butyllithium is very, very strongly basic. The pK of an alkane is about 50. pK of diisopropylamine, we already said, is 40. That equilibrium lies way, way to the right. You might ask, why don't we use butyllithium as a base? Comes back to what I was saying about sterics. If I use butyllithium, the main reaction, the only reaction that you would detect, that you would write on, say, an exam, if you want to get down to the brass tacks of being an OChem student, would be addition of the butyllithium to the carbonyl. It's not sterically hindered enough to not add. We go to lithium diisopropylamide with those big isopropyl groups, and now it's much more basic than nucleophilic. The N-butyllithium toward a carbonyl is much more nucleophilic than it is basic. All right. Let's have some fun now with variations among enolates. So, let's imagine we have our methyl cyclohexanone and we treat it with base. Now, we can get two different enolates. We've got two different types of alpha protons. We've got alpha protons that are opposite the methyl and alpha protons that are next to the methyl. In other words, we can get this enolate, or we can get this enolate. The less substituted enolate or the more substituted enolate. Now, in general, we know that more substituted double bonds are more thermodynamically stable. The more substituted enolate is what we call the thermodynamic enolate. It's lower in energy. Among an equilibrium between the two enolates, it would form. But we also know that size matters. We have a bulky side of the molecule, we have a non-bulky side of the molecule. If a base, particularly a sterically hindered base, needs to get in to pull off a proton, it's going to grab the easier one if it's bulky. So, the enolate that is less substituted is often referred to as the kinetic enolate, the one that forms first, the one that is easier to form. So we can go ahead and think of it as these protons are more accessible to base. But this proton is technically a little bit more acidic. So I will write here just so for comparison, more substituted enolate, more thermodynamically stable. So let's take a moment to play with this notion because, as I said, organic chemists love to control reactions, love to control reactivity. And it's important because when you're making molecules for medicines or for drugs, you need the molecule that you want. And I'll take a couple of examples from your textbook here because they're good examples. If we take our methyl cyclohexanone and we treat it with LDA and THF at -78, you may see it written just as LDA, you may see it written as LDA, THF, you may see it written as LDA, THF -78, and we treat it with methyl iodide, we deprotonate to form the kinetic enolate, and we end up with the 2,6-dimethyl cyclohexanone. It's all right via the kinetic enolate. Borrowing an example from your textbook, which if you want to ask questions about after class, I will tell you some of the subtleties of. But if you treat with a weaker base that can equilibrate, your textbook uses sodium ethoxide in ethanol. And basically, the way I will write this is to mix sodium ethoxide, methyl iodide in ethanol. Then, because we're under conditions where we're thermodynamically equilibrating our enolates, your predominant product, your main product, is going to be the 2,2-dimethyl cyclohexanone via the thermodynamic enolate. And so this is a taste of the type of control that organic chemists can get. And I'll write this as major product. Technically here, if I do this reaction with LDA, this is the major product. In other words, I'm going to get 99 parts of this and 1 part this. Technically, this is the major product. I'll probably get about 80 parts of this and 20 parts of that. No, there's one question, but I want to wrap up with a couple of last points about stereochemistry and stereoisomers at this point. Because I think it's pretty, and I think it's cool, and I think it's intellectually deep, and I think that a lot of this is what organic chemistry is all about. So technically, I'm lying in that structure, or maybe to be more precise, I'm telling you half a story. And the other half of the story is when I draw this structure, I'm living in flatlands. Each of those carbons with a methyl group is a stereogenic center. And so we have different types of species that we can get. We have the species, the stereoisomer, to be more specific, in which the 2 methyls are on the same side of the ring. We have the cis stereoisomer. We have the stereoisomer in which the 2 methyl groups are on the opposite side of the ring, the trans stereoisomer. And so when we form our enolate, and now I will specify my methyl stereochemistry, if our methyl group adds from the back, we get the trans stereoisomer. If our methyl group adds from the front, we get the cis stereoisomer. And there's one more level of subtlety. And I'll show you that, and then that's going to wrap up today's lecture. So imagine for a moment I take this compound, and almost invariably it's going to be racemic if I haven't specified otherwise. And so I treat with LDA in THF at -78 degrees, and then I treat with methyl iodide just as I've done. And you'll get a mixture of the cis and trans compound. But of course, the trans compound is going to be the racemic. In other words, we generate our enolate, and the methyl group, if it adds opposite the methyl group, depending on whether this methyl group is out or back, we're going to get the racemic compound. In the case of the cis compound, if it adds from the same face, the cis compound is a meso compound. So in other words, whether I draw it like this or I draw it like this is just the self-same thing. All right, well, that gives us a taste of the richness of stereochemistry as well as a beginning on this notion of control. And you can see, even though we've talked at this point about control of the regiochemistry of addition, we've only seen that there is still a depth and richness to the stereochemistry of addition, and that will go largely beyond the scope of this class. Thank you.